Hi everyone, welcome to our second week of CSE307 during the summer of 2018 at Stony Brook University. We are going to continue today with SML, with the second lecture of SML. You may know a little bit of SML from our previous courses, CSE215 at Stony Brook. However, today we are going to talk about more advanced topics in SML, in functional programming in general and in SML in particular. So recursion is very powerful, and last time we talked a lot about recursion, how to implement problems recursively, and we also talked about basically data structures, a little bit about how data structures are structured in SML as basically composed data structures, composed lists. We also talked about a little bit about patterns. Patterns is also a very powerful feature. It efficiently implements basically detecting patterns in the input stream, also creating outputs based on these input patterns. But today we are going to go into the third, or probably the most important feature and most powerful feature of functional programming languages. And those are the fact that parameters to functions could actually be also functions. The return results of functions can also be functions. So we are going to talk about higher order functions. Even if you understood probably SML or the nature of SML, the fact that you can write everything through recursion and is a very powerful feature of programming languages like functional programming languages, probably you didn't get into details about higher order functions. Higher order functions are very powerful and at the same time quite complex and difficult to understand features of functional programming languages. Maybe the most powerful feature of functional programming languages, because of the fact that is used so much in distributed computing these days, like in MapReduce. Today actually we are going to talk about the function map. That is the common feature of all of these distributed computing paradigms. So in functional programming languages, functions can be used in the definitions of other functions. And these other functions that use basically parameters of the type functions are called higher order functions. And most representative in this set of higher order functions is map, which takes as the first argument a function, and as a second argument a list of arguments, and it will apply this function on all of the arguments in this list. Of course, we have to be careful that the type of the arguments in this list are of the same type of the type of elements of this list is the same type of the input to the map function, or to the first argument function to this map function. So here we can see the definition of map. Is very simple. It basically takes two parameters, a function f and a list of arguments. If the list is empty, there is no more element to apply the function f to, it returns the empty list. Else, it applies the function f on the first element, and it counts that to the result of the map function of the function f to the tail of the list L. So basically we can take a look at the definition of the function map. So the domain of the function f is the Cartesian product of those functions that can be applied to elements in the domain A with the result in the codomain B, with a list of the elements in the domain A. So we can see that the type of elements in the second argument of the map function must be the type of elements in the function that is the first argument of the map function, with results in the codomain that is a list of elements of the type B, which is the codomain of the first argument of the map function. So basically it applies this function f on a list of elements of the same type with the domain of the function f, and it returns a list of elements in the codomain of the function f. Simply, we can define a function square that takes any integer x, and it returns the product of x with itself. So we can see here that basically this is a function from integers to integers. Therefore, if we apply the function map on the square function with the list of elements 2, 3, 4, a list of integers, it returns the squares of those three integers. So it applies that function square, which was an input to the map function, on every one of the elements. And earlier, before the lecture, I actually implemented these three statements in SML. So first I implemented the map function exactly the same way that you see it in the lecture notes. It returned that the fact that map is a function from the domain A to the domain B with the Cartesian product of a list of elements in the domain A, and it returns a list of elements in the domain B. I implemented a function square, which returns the square of any integer x, and then I applied map on the square and the list of integers, which basically applies that function on every one of the elements of the second list. So, of the second argument, which is a list. So we can see that it's relatively simple. Basically, it's a function that takes other functions as inputs. We will see later today that there are many other functions that return other functions as input. So in fact, the function itself can return as a result other functions. And one feature of functional programming languages, which we'll again see in a couple of seconds, is called carrying. It's named after Haskell Curry, the mathematician and logician. And basically it applies, if a function takes multiple arguments, we can pass only part of these arguments, like the first argument to this function, and the result of the function application is in fact a function that applies on the rest of the arguments. This carrying is a very useful feature, especially used in the composition of functions, because you apply a function, the first function, you return a function that will be composed with other functions. We'll see in a couple of seconds what do I mean by that. So let's see a few more examples of higher order functions, and then we are going to use higher order functions to define permutations. Permutations is a very complex method that we will see in a couple of seconds that actually makes use of the mapping function at least twice. So let's see more examples of higher order functions. In this example, we also add another feature of functional programming called anonymous functions. The fact that we can create on the spot functions on codomains, on domains that take values in domains and return results in codomains, and these functions are not named. We don't need them again. Basically, we just use them maybe in the definition of other functions, and they will basically be defined and returned on the spot, and they will be used in those new functions. So let's see, for example, an application of map. This map function, which we defined before, takes as an input an increment function, which is defined in line. It's an anonymous function. It's a function that for every integer x, it returns x plus 1. So it's very easy to define in this function another function. So it applies this increment function on the list of integers from 1 to 5, and it returns each one of the integers in that list incremented with 1. The increment function that we have below, it actually uses this definition of the map function by defining a new function, increment, that is equal with the result of the map function applied on this anonymous function that increments every element with 1 on a list of elements. So we can see that we can use anonymous functions also as part of the definition of other functions. So when we don't need that function again, maybe we don't need the increment function again, we can actually define and use the anonymous function in the current function. And here we have an example of the increment function that takes a list of the arguments from 1 to 5, and it actually returns each one of those arguments incremented with 1. Moreover, if we define, for instance, the McCarthy-91 function, which many of you have seen in CSE114 and CSE215 at Stony Brook University, we can actually see the feature of this function that for every value less than 100, it actually converges to 91. So we first define the classical definition, standard definition of the McCarthy function, McCarthy-91, apply to any integer n. If n is greater than 100, it returns n minus 10. Else, it returns McCarthy-91, apply to McCarthy-91 of n plus 11. So we can see that applying this function McCarthy-91 on this list of integers 101, 100, 99, 98, 97, 96, and so on, in fact any value less than 100, it will actually converge to 91. So you can actually apply the function above to see what happens for any one of these values. The easiest would be 98, because you will see that 98, because n is less than 100, will be McCarthy of 98 plus 11, which is 109. And that will be McCarthy of 109 minus 10, which is McCarthy of 99. So you will see that for every integer less than 100, McCarthy of that integer will be equal with McCarthy of the next integer. So McCarthy of 98 is equal with McCarthy of 99. And then applying again to McCarthy of 99, that will be equal with McCarthy of 100, which will be equal with McCarthy of 101, which will be equal with 91, because it's the base definition above. So it's easy actually to see the features of multiple recursions with the map function, because you can apply that function not only to one value, but to multiple values. And now you can see that you can actually draw graphs which, in the Cartesian plane to see how a function evolves over time by applying that function on multiple values in a range. And this is quite useful in many functional languages that are used in mathematics. So one thing that you see, at least in the use of this example below, is the fact that we apply map on the McCarthy-91 and on this list. But we don't use the parentheses. In fact, the fact that map is a function that applies on multiple arguments, it will apply map on McCarthy of 91. So now the result of that will be a new function that takes as an input a list and applies the McCarthy-91 function on every one of the elements of that list. And that is the feature that I mentioned a little bit earlier, called carrying. And we are going to talk in detail about carrying in a couple of seconds. Let's stop for a few seconds to see if there are any questions in the chat. So I will return to the chat. I see that there were a lot of questions today, and I will respond to these questions. Let's see if the TAs responded to any of these questions. So Daniel has two main questions. Meanwhile, I will read the previous questions asked by other students. So Adam is asking about the homework. I will address this after the lecture today. I think basically the idea is that we want to follow the same ACM features that we have defined in the ACM contest. We want to take the inputs exactly in the same format. The input has to specify the number of tests or the inputs on which we apply these problems. Most of these cases in our tests will be just one case. So the first line is usually just one, followed by the actual input. There are more questions about the homework, if they are opening, if the files are opened with read mode. Yes, of course. I will respond, as I said earlier, all of the questions about the homework in a separate video today. So don't worry, there is no problems about the questions about the homework. I will respond to them a little bit later after the lecture. The lecture will be recorded and posted on YouTube like we did for the Python lecture. and I don't want to mix too many things in the same lecture. There is a lecture on SML, or basically the second lecture on SML, and then we'll continue with other lectures that address syntax and parsing and tokenizing, and then we are going to address also the homework with all of the issues that may arise in the homework. Okay. So another use of the map function, or basically a different function that is a higher order function, also very useful, is a standard function in higher level functions, is called filter. Filter is the application of one function on all of the elements of a list, and basically filtering out elements that do not satisfy the input function that is passed as the first argument of the function filter. So first, let's define the function filter. The function filter takes as inputs a function f and the list. If the list is empty, it returns empty. There are no more elements to filter from that list. If the function f applied to the first element of the list, the head of the list, is true, so we can see that this function f is a function defined on the elements of the second argument list of the filter function, with results in Boolean. So the codomain is Boolean. It will basically return either true if the element satisfies the function f, or false otherwise. So it applies the function f on the head of the list. If the result will be true, it returns the head of the list, calls the rest of the applying the function filter on the tail of the list L. So we call again the function filter on the same argument function f and the tail of the list L, or just the result of that filter on the function f and the tail of the list L. So what we can see is that it basically keeps from the input list that takes elements from the domain A, those elements from the domain A in a list that satisfy the function filter. So applying filter on an anonymous function that takes every element x and checks if x is positive, basically it returns true only for the positive elements, or the elements strictly greater than 0, on a list of elements that contain negative elements. Tilde stands for negative unary minus in SML. So applying the positive check for elements on a list of elements that may contain negative, 0, or positive numbers keeps only the list of positive numbers in that list. So it's similar to the map function, only that the map function applies a function on all of the elements and returns the list of mappings, with where the filter function checks if any one of the elements in the second argument satisfy the function that is the first argument, and keeps only those elements, deletes all of the other elements. So now we can write a very complex function using the map function. So now you will see the power of the map function. So first, we have to remember what permutations are. Permutations are all the possible orderings of the elements of a list. So we basically will want to find all the possible orderings of the elements of a list. And there is a recursive algorithm that you may have seen in Java or other programming languages, which basically does this recursive algorithm, keeps all the possible permutations. It takes one element out, each one element out, then it computes all the possible permutations of the other elements in the list, and then for every one of these permutations, it inserts the element that was taken out at the beginning in every possible interleaving in the permutation. So now, let's say that the original list was 1, 2, 3. We take first 1 out, then we compute all the possible permutations of 2, 3, which is 2, 3, and 3, 2. And for each one of these permutations, it inserts 1 now in every position possible in this permutation. So let's take, for instance, 2, 3. We can insert 1 before 2, between 2 and 3, and after 3. So now we basically need in SML every helper function that you define, that you use in a follow-up function. You have to define it first. So first we are going to define the helper function interleave. So interleave takes an element x and a list, and it returns all the possible lists where x is inserted in every possible position in the list that is passed as the second argument. So now, for instance, if we have the empty list, x can only be inserted in that list, so we get the list that contains x. So interleave, since it basically returns all the possible such interleavings, it returns the list that contains the list x. So the list x is one interleaving, is the only one interleaving, and now we are getting the list that contains that list x. Now let's see what happens if there are more elements in the second argument. So if x is inserted at any possible position in the list that contains h and as the head and the tail t. So one possible interleaving is to have x at the beginning of the list. So x cons h cons t is one such interleaving. And since the cons operator is right associative means that it will first construct the list that contains h cons t, and then to that list it will insert x at the beginning. So the first possible interleaving is x is the first element, h is the second element, and it ends with the tail t. So basically we have one list of the same type of elements created. Now we are consing this list, so the result of my interleaving are all the possible interleavings of x in the list ht, or the second argument. So it consists this to the result of map applied to the next two elements. So first it computes all the possible interleavings recursively of x and t. So basically recursively the same definitions will be used to insert x at every possible position in t. The first one, the first interleaving that we will have will be x followed by the list t. That will be one interleaving that misses h. So for every list that we are getting in, basically my interleave returns a list of lists. For every argument or for every element in that list, which are all the possible interleavings of x and t, it adds h at the beginning. So the first argument of map is actually a function that for every element returned by my interleave creates a new list that starts with h, and then the tail is the list L. So this map function basically creates, inserts h at the beginning of every one of the lists created by interleaving x with t. So let's actually think of what's basically happening by looking at a few examples. We kind of understood, I hope, in essence what this function does. It basically, for every interleaving possible, it adds h at the beginning of that interleaving. But let's actually see that on examples. So first we have one element, 1 interleaved with the empty list. As we had the base case before, it will return a list that contains the list of 1. Because there is only one possible interleaving, we put 1 at the beginning. Let's see what happens with my interleave of 1, 2. First, what do we expect? We basically expect that 1 will be inserted in every possible position in the list that contains 2. That will be before 2 and after 2. And the result of my interleave, which returns all the possible interleavings, will be the list that contains the list 1, 2 and the list 2, 1. So let's see how did it compute that. So first, this is not the base case. We are looking for interleave that takes one element and a list that contains at least one element. So my interleave takes 1, x is bound to 1, and h will be bound is the head of the list that contains 2. So H will be bound to 2 and T will be empty list. First result that will be returned in that list of lists will be 1 const 2 const the empty list, which 2 const the empty list is the list that contains 2, and 1 const the list that contains 2 is the list 1, 2. So the first list is returned in that outer list, in the double, in the outer list. Now we apply the function map on the result of my interleave of 1 and the empty list. My interleave of 1 and the empty list returns the list that contains the list 1, basically the previous this example. Now for every one of those lists, which is just one, in fact, the list that contains 1, adds 2 cons that list 1. So it adds 2 at the beginning. So now 2 cons the list 1 is 2, 1. That is the only result returned by my interleave of 1 and the empty list. So therefore the output of my interleave of 1 and the list 2 is the list that contains 1, 2 and 2, 1. Now let's go to a more complex example. So my interleave of 1 and the list that contains 2, 3. First will return, is this case, it will return the list 1 followed by 2, 3. So it's 1, 2, 3. Then it will call my interleave of the list 1 and the list 3, which basically will create 2 interleavings, 1, 3 and 3, 1. Map will add 2 at the beginning of each one of those interleavings. So now we will have 2, 1, 3 and 2, 3, 1. If we are looking at the original function, basically it inserted 1 before 2, between 2 and 3, and after 3. So we are getting all the possible interleavings of 1 in the list 2, 3. So what can we do with it? Also, we need other helper functions, like for instance append all, that will append multiple such list of interleavings. We will take a look at the append function in a couple of seconds. First, we need to actually go to the import to the main function permute. So let's remember what permutations does. Basically, we look at this example first. Permutations is supposed to return all the possible permutations or orderings of the list that we get as an input. So for instance, if we would compute the permutations of 1, 2, 3, those will be the permutations of 1, 2, 3, 2, 1, 3, 2, 3, 1, 1, 3, 2, 3, 2, 1, and 3, 1, 2, and 3, 2, 1. So basically there are all the possible orderings. Now, we may be used with other ways to write it, but this is in fact a set, so it doesn't really matter that we collect these permutations by putting first 1 at the first position, like in 1, 2, 3 and 1, 3, 2, and then 2 in the first position and permuting the rest, so it would be like 2, 1, 3 and 2, 3, 1, and then 3 first element and returning 3, 1, 2 and 3, 2, 1. This is a set, so in fact all the permutations are returned by the permute function. So let's see how do we do that. So as I said earlier, we can compute it recursively. First, we need a base case. Permute all the possible permutations of the empty list is just the empty list. Basically, we return a list that contains the empty list. Otherwise, we define this function with patterns. Permuting a list that contains at least one element, we'll call the function append all, which appends all the results returned by the inner function map, which basically returns a list of lists, and then the function map. So the function map applies to an anonymous function, which for every possible permutation of the tail of T, calls my interleave of H and that list. So let's first understand bottom up what happens in this example. For computing all the possible permutations of the list H const T, which basically is all the possible permutations that can be built first by in the tail, and then inserting the head in every possible position in the result, in the permutation. So it first computes any single permutation of t, recursively, which will basically return all the possible permutations in a list. Then, for every one of those permutations, the map function will insert h in every possible position in those permutations. So let's take the example that we had below. We first compute all the possible permutations of 2, 3, which is 2, 3, and 3, 2. For every one of those, like for instance 2, 3, it inserts the first element, which was 1, at every possible position. So it inserts 1 before 2, 3, 1 between 2 and 3, and 1 after 2, 3. That will give us 4 possible permutations that are different. Another permutation of 2, 3 is 3, 2. So for every one of those, for 3, 2, it will insert 1 before 3, 2, 1 between 3 and 2, and 1 after 3 and 2. And that gives us basically 2 lists of permutations. So at this point we have to flatten, or not really flatten because we only flatten one level. We have 2 lists of permutations. We have to append them, but in most cases we'll have the result of these permutations many lists. So we have to basically go down one level, flatten one level. So the append all function takes a list of lists, which internally contain other lists in this example, but in more general case it's just a list of lists, and appends all of those lists. So again, we write it recursively. We can see here one example. Basically, we get a list of lists, and we basically append the inner lists. So we get a list of the actual permutations, 1, 2, and 2, 1. So the append all function applied to the empty list is empty, and applied to a list that contains inner lists z as the head and a tail that is list of lists will concatenate or append z to the result of append all on the tail zs. So we'll basically go down one level to append the permutations. So we see in this example permutations that we use the map function twice. First, we used it to actually eliminate the complexity of interleaving by interleaving one element in all of the possible lists that we get as interleavings of x with the tail. And then we again use the map function in the same way to actually, for every possible permutation, to call the interleaving. So in these examples, we actually are developing a quite complex program that uses higher level functions. In fact, we can see that we are also using anonymous functions, at least in 2 cases. So let's see if there are any questions. This is a function that takes a lot of thinking to actually understand that it's in fact correct. So we'll stop for a few seconds to see if there are any questions in the chat. Any questions about higher level functions used in the definition of permutations? The @ sign stands for append. So we defined earlier in the last lecture the concatenation function, and we basically use the append function. So concatenation of lists, because it's a very common method used in concatenation of lists, has an SML, a built-in operator denoted with the @ sign. The @ sign has exactly the same definition that we used for concatenation earlier. Basically, it stands for concatenation of 2 lists by doing it recursively eliminating one element from the head of the list X, calling recursively concat on the tail of the list and Y. So in SML, there is a built-in operator for concatenation because of the fact that concatenation is so common, and that is the symbol at. Okay, so if there are no more questions, I will return to the lecture. So as I said earlier, the fact that in many cases we don't use parentheses around the arguments is the fact that in SML you can apply a function on the arguments of that function in order of occurrence of those arguments one by one. So in fact, when we define a function f applied on a, b, and c, we actually are defining a function that applied to a returns a function that applied to b returns a function that applied to c returns an integer. So in fact, the function f is not a function defined on the Cartesian product of three integers, but really a function that applied to the first argument returns a function that now applied to the second argument returns a function that applied to an integer returns an integer. But this applies to every function with multiple arguments. And here we actually have an example. The same function that we defined above can be defined without parentheses. It has the same meaning. And it returns the sum of a, b, and c. And we can define a new function that takes the result of function f applied to 1. And now we can see that this increment function is really a function that takes the next of the two arguments, in this case 2 integers. That takes the next integer. Again, we can actually get increment of 1. The previous function applied to 2. It's a new function. Let's call it increment of 2. And increment of 1 and 2, this new function is actually a function that applies to the third parameter. This was named by Haskell Curry. He stands for the the functional programming language Haskell, that some of you may be familiar with. Another functional programming language also very popular. The same with like Lisp and Scheme. Those are also functional programming languages. And it has this feature that you basically can apply the function on only a certain amount of parameters. In fact, this is called partial application of functions, and it was reinvented by many other programming languages, including Java. Java 9 and Java 10, in fact, have internally carrying. So you can define functions applied to other functions that return functions as parameters. In fact, one feature that I currently cover in my honors computer science 2 class is streaming. Streaming is this feature that you can apply on a collection multiple functions recursively or in a stream. It's a very powerful feature that if you want to learn more about, you can read my lecture notes for CSE307. Also, we can compose multiple functions, and this is exactly function composition that we have in many other languages. And in this case, we actually can define some function definitions. So composition applied to two functions, f and g, applies the function f on the result of the function g on any element of x. So in fact, we can actually apply the composition of the two functions, and we get a new function. So the function f is the composition of sinus with cosinus, and is in fact a function from reals to reals. It's a function that takes elements in the domain of the second function g, and returns results in the codomain of the function f, because the function f has as domain the codomain of the function g. So we see that in fact the composition function takes two functions, a function that applies to the domain A returns values in the codomain B, with a function that takes elements in the domain X and returns elements in the codomain A, because the function g codomain must be the same with the domain of the function f, and returns a new function that takes inputs in the domain C with results in the codomain B, the codomain of the function f. So now we can actually apply the function f on elements, and it will apply sinus on cosinus of the element x. So in fact, if you apply f of 0.25 radians, it will actually apply the cosinus function and then the sinus function on the result of that cosinus function and return this value. And we know that composing sinus with cosinus is the same with composing sinus with cosinus with the composition function that is a predefined operator in SML. It's exactly the same. You can see that the two results are the same. So this is another symbol similar to the @ sign that was asked. There was a question a few minutes earlier, and it stands for this composition of functions. And we also see currying in this example, the fact that we can use the function applied on the first arguments, and that returns a function that we continuously can apply on other arguments, the rest of the arguments of these functions. So this really shows the power of higher level functions. Not only the fact that you can pass functions as parameters, but the fact that you can also apply, you can return functions as the result of functions. So you basically can apply those continuously on other arguments. Now, before we continue with even more features like mutually recursive functions, where you define two functions that are depending on them the result of themselves recursively, let's see if there are any more questions. So these are features that probably you didn't cover, like carrying and composition of functions, and higher level functions like map in CSE307. In fact, CSE307 is just the first level of application of functions in programming languages, from foundations of computer science like functions, mathematical functions, to programming languages. But now you can actually see the power of higher level functions and other features like currying. So any questions before we continue? Good. So mutually recursive functions are actually just more examples of using recursion and functions. So we want to define two functions, odd and even. And we don't really want to define them mathematically, each one independent of each other. We want to define them together because we know that every odd number is followed by an even number, every even number is followed by an odd number. And in fact, exactly the opposite, the fact that every odd number is preceded by an even number. So odd integer n is odd if n minus 1 is odd, and every integer n is odd, it's even if n minus 1 is odd. So now, how do we define these in SML? If we have mutually recursive functions, we can define them together, all of them, into a definition that uses the connective AND for the definition of the multiple recursive functions. So first we define odd. We need, in all of these recursive definitions, a base case and a recursive relation. So a number is odd of integer n. If n is equal with 0, then it's false. N is not odd. 0 is not odd. Else, n is odd if n minus 1 is even. Similarly, we define even. N is even. If n is 0, we return true. If n is 0, then even is true. Else, the even of n is even if n minus 1 is odd. So the result of this definition in SML will be that both odd and even are functions from integers to Boolean. We basically have, like in the filter function, a function that returns in the codomain Boolean to basically check if the input satisfies the domain or not of this function. Not really satisfies the domain, but basically checks a function, the correctness, or if that fits a specific function. So let's see what happens for even of 1. 1 is different than 0, so it will call odd of 0. Odd of 0 returns false, therefore even of 1 returns false. Let's see what happens of odd of 1. Odd of 1 is different than 0, so it calls even of 0. Even of 0 returns true. So odd of 1 returns true. So this will happen for every number. If you call odd of, let's say, 9, it will call even of 8, which will call odd of 7, which will call even of 6, which will call, and each one returns the result of basically the function that gets called. And finally it will get to even of 0, which returns true, and all of the functions on the recursively defined functions are true. So odd of 1 is true, even of 2, odd of 3, even of 4, and so on up to odd of 9. So we will use exactly the same idea for one of the classical sorting functions. So this sorting function is called merge sort. We will define a function that sorts a list of integers. You can define it on a list of reals if you want. This function is recursive and is based on the well-known method called merge sort. To sort a list of elements L, first we need to split the list L into two disjoint sublists of about the same size. Basically, we split the list by putting the odd elements into one list and the even indexed elements into another list by taking one element out of each one of the two functions, of the two successively recursively, mutually recursive functions. And then recursively we sort the sublists with merge sort, which actually will do in half with the size of the list. And finally we merge the now sorted sublists into one single sorted list, and we can do this in linear time. The advantage of this method is that sorting any list of n elements will take a time equivalent in the size of the list, let's say n, multiplied with logarithm of n. This method is known as merge sort, as I mentioned earlier, and it will require functions for splitting the list into two sublists. We'll call these functions take and skip. And then we are going to merge the two sorted lists into one list using another function for merging. So splitting will be done through two mutually recursive functions called take and skip. Take will invoke skip, and skip will invoke take, each one on the tail of the original list. So we are going to split this list using these two mutually recursive functions, take and skip, which alternate elements, and the elements at odd number positions will be taken in take, and the elements in the even number positions will be taken in skip. The definitions of these two functions mutually depend on each other, and as we saw in the previous example, we are going to use the SML keyword AND to join the two definitions together into one definition. Again, if you remember, we said that any function in SML can only use functions that were defined before. But we cannot define any one of these functions first, because take depends on skip and skip depends on take. So we have to define them both at the same time. Then they only depend on each other and on nothing that was defined before. So let's see the definition of take. Take of a list L. If the list L is empty, returns empty. That's the base case. There is nothing else to be invoked on skip, and there is nothing else to be returned by take. Else returns the head of the list, so the element at an odd position at index 1, or the first element of the list, cons the result of skip on the tail of the list L. What exactly skip does? Skip skips the first element and returns the second element, cons the fourth element, and so on, the elements at even positions. Let's see the definition of skip. So skip takes a list L. If the list is empty again, there is nothing else to be returned, so it returns also empty. Else, it invokes the function take on the tail of the list L. So it actually skips the first element because it doesn't return the head of the list, but invokes the head of the take method on the tail of the list. So it will return the head of the tail of the list as the first element. And then it will return the third element, the fifth element, and so on. So take will return all of the odd indexed elements, basically the first element, the third element, and so on. Skip will return as the first element the second element because it invokes take on the tail of the list, and then the fourth element, and so on. So both lists will return also, both methods will, functions will return also lists of elements. But one returns the odd indexed elements, the other one returns the even indexed elements. So for instance, if we invoke the take method on the list 1, 2, 3, 4, 5, 6, 7, it will return the list of elements 1, 3, 5, and 7. And you can actually see recursively how it does it. It keeps one calls skip on the tail, which is from 2 to 7. Skip will ignore the first element and it will call take on the rest of the elements from 3 to 7. Take again keeps 3 and then calls skip on the rest of the elements from 4 to 7. So the first two elements we can already see them. Take returns 1 and 3. And it continues with the odd indexed elements. Skip, on the other hand, returns the even indexed elements. So it calls take on the list, on the tail of the list, which is 2 to 7. Take will return 2, and it will call skip on 3 to 7. Skip will call take from 4 to 7, and it will return 4, and invoke skip on 5 to 7. Skip will invoke take on 6 to 7. Take will return 6, and we will call skip on 7, which will call take on empty, which will return the empty list. So we'll see that basically it returns the even indexed elements. And now if we sort the two lists, we can actually merge them in an order. But for that we need to define a function merge. So merge takes two sorted lists and merges them. Compares only the first elements, because by transitivity all the other elements are greater than the first two elements, than the first elements in each one of the two lists. Now, what are the base cases? The base cases are quite simple. If either one of the two lists are empty, first argument or second argument, returns the other argument. So merging the empty list with any list is the other list. Merging any list with the empty list is the first list. Otherwise, the most general case is when we have at least one element, x and y, in the two lists. And then the rest of the elements, let's call them xl and yl for the tails of the two lists. So first thing, we are going to compare x with y. If x is smaller, then we keep x at the beginning. It's the smaller of the two, and by transitivity is smaller than the elements in the first argument, the tail of the first argument, and since it's smaller than the first argument of the second list, is smaller than all of the elements in sorted order in the second list. So we keep x as the first element, and we const it with the result of merge on the tail of the first list and the second list. So that will give us a sorted list with the elements in the rest of the two lists, and we have x as the first element. So we can see that basically we change the index, we now move to the second element in the first list, and we call merge recursively. Similarly, if x was no less than y will be kept as the minimum element at the beginning of the result, and it will call merge on the first list, complete first list, and the tail of the second list. So now we'll basically call merge on the rest of the list to merge them in a sorted order, and we use the const function in order to insert y at the beginning. So passing sorted lists to this merge function will actually return a sorted list in linear time. And it also works on the base cases with either one of the two lists empty. Finally, we can implement the merge sort method as a function as the sort method. So sorting of a list L, if the list L is empty, we return the base case, the empty list. If the tail of the list L is empty, then we return the list L, and we will see that the reason for that is that if we don't do this other base case, we are going to call sort on a list of one element to infinity. So we have two base cases, and those two base cases check that either the list is one element or no elements whatsoever. In that case, is sorted by default. Otherwise, we call the merge function on the results of sorting the result of take from the list L and skip on the list L. So we sort the odd indexed elements, we sort the even indexed elements, and then we merge the two lists. So let's see that this second case is actually necessary, and we can actually combine it with the first case. We can write an and also the list is the tail of the list is empty, then return the list L. So if we have one element in the list, and let's say that we do not have this second case, this case is not there. Now we will call merge on sorting the result of take, which will basically call sort on the list of one element, which is exactly with the first case. So we need to have another case that says and also the tail of the list L is empty, or else. It's either that the list is empty or else the tail is empty, then we return the list L. So this is the base case, and in fact if we call it on any list that is, let's say, unsorted, let's find an example, we call sort on 7, 4, 5, 2, 1, 6, we return the sorted result value, and this value will be equal with the list in sorted order. In our case, we have 1, 2, 4, 5, 6, 7. So let's see this example with the new function that we just defined. Again, in the SML interpreter, you can always define it at any point that you want. We didn't define take and skip. We need to also define those. So let's define them directly from the lecture notes. First we define those. We need also to define the merge function. I will use the definitions with patterns from the lecture notes. And finally the sort function as we defined it in a few moments ago. And now we can actually call sort on the same input that we had before. So it returns that indeed this is the sorted list, and let's put that in the lecture notes for later. I will update the lecture notes and put them on the course website at www.cs.stonybrook.edu/CSE307. Let's see if there are any questions up to now. Please let me know if you have any questions. I believe that I already forwarded the old website. to the new class. So www.cs.stony.edu, CSE307 should forward to the summer edition of this class. So it's currently forwarded to our website, where basically covers SML. And today we are also continuing with principles of programming languages, the second chapter in our textbook, which is on programming language syntax. We'll learn how to write tokenizers. We'll learn how to write parsers in Python using the classical Lex and Yak parser generator tools. And we basically will write a programming language from scratch. But we'll do this slowly with a slow pace in this class. Yes, it will take you to the summer CSE307 class. Okay. Excellent. So, just to finish SML and basically topics about SML. SML is a fully fledged language. You have strings, characters. You can basically do concatenation of strings, complex methods with strings. These are important for actually defining basically patterns for not only lists but also for more complex examples. If you take problems from any website that is used for preparing for interviews, like Topcoder or CodingBat, you can actually implement those problems directly with the string and character types. I will not go into details because these are not actually required for our exams or any kind of like problems in this class. But in the lecture notes, you will also find methods for strings and methods for concatenating strings. So the rest of the lecture notes that you will find are just 3 slides about more topics on SML. I will not go into details because, as I said, the important issues in functional programming languages are not actually writing these kind of algorithms with strings and complex data structures, are recursion, the fact that we can use patterns for defining functions, and the fact that functions can take other functions as inputs, and they can basically return other functions as outputs, and also the feature of carrying. These are important for functional programming languages, and the rest are just basically same features that occur in other programming languages. So at this point, if there are no more questions, I will finish the lecture for SML, post it on the course website, and also post the recording on YouTube later today, after we record it from SB Connect, which is Adobe Connect, into MP4. And we'll continue in a few moments with syntax and basically writing parsers for programming languages. So thank you, and stay tuned.